Oh, hello. Why, yes, this is a Zoom screen recording. Hopefully, I didn't give any of my regular students PTSD. I thought we were watching a YouTube video. Why is it a Zoom lesson? Well, it's because I'm trying something a little bit different today. I'm doing a bit of math for teaching, which hopefully isn't poor. And yeah, so I'm doing it over Zoom because I think it will be the easiest way to share my screen and the questions and the Zoom scribbles with the annotate at the same time, which also means I'm going to have to do all of this one take. So let's see how that goes. There might be a lot more and R while I think of the right thing to say. All right, here we go. So share screen. Right, so first of all, a couple of thank yous. Yes, this is a picture of myself. So back when I was doing Wilfred Owen, the video, someone in the comments who I've actually never met because it's the friend of my media manager, Anna, made a comment of hey, I might do meth one day, channel my inner Eddie Wood. I always thought that was funny, so I just got to give a very late thank you for that hilarious comment, because at the start of that video, I did say I might do math one day, and today is that day. So my prediction has been realized. And I would like to give a thank you to Brooke, who is one of my English and math students, for giving me the idea for this lesson. So she brought me a ton of questions for when she was doing trial practice, and she thought those questions were a little bit more difficult and required some explanation. And the questions she picked, they were all very interesting in their presentation. So while I talk about those, hopefully you guys can learn some exam tips on how to approach questions that are a little bit unusual in their presentation. Right, so here are the bunch of questions that Brooke has brought me, and we're just gonna go over them. Oh, actually, recently, for those of you who actually know Brooke, it's Brooke X. X is not the unknown quantity here. It's the starting letter of her last name. Recently, she actually achieved something that I personally never achieved in all of my English studies at school. So if you do know her personally, go ask her what that is. All right, on to the math, or meth, depends on how well I pronounce this. So for the math, today we'll mostly be doing sequence and series. So that's what the title of this video will be called. But we're just going to start out with a calculus question, because I do think this is quite a good question. Oh, you can see the tip I wrote for. When finding the same thing two different ways, you treat both answers as equal to each other. All right, we're going to find out what that is. So for those of you who might not be in Year 12, or maybe might not even be in advanced maths, you're probably not going to watch the rest of this video, but please don't let this video put you off choosing advanced maths in years 11 and 12. It is a little bit harder than standard maths, but I do think that doing advanced maths opens up more doors when it comes time for your UAC university preference selections, because quite a lot of degrees, especially in STEM, and even really not in STEM, anything that requires more complex calculations, a lot of those degrees will have prerequisites of advanced maths and not just maths. So please consider it. And if you like to, if you like some help with deciding exactly which topics to pick, feel free to have a chat to me about it, because I do like to talk to you about that kind of stuff, career guidance and subject selection and things like that. All right, here we go. So we have a calculus question just to start off. And then when you get these booklets from your teachers that have a collection of past HSC questions sort of by topic, you can see anytime you see a little lightning bolt, you should probably know it's going to be a hard question coming up, right? So they have RAP data. RAP is reporting and performance. It's like this metric for teachers. So when you see these numbers, bottom 22%, 13% below the state average, so you know that everyone bombed this question, so it's probably quite hard. But I'm going to break this question down, and it might not be as hard as you think. So find the exact value of the integral between pi 3 and 0 of cos x dx. So the first one is just using the integral sheet. So for those of you who do calculus, well, what's this doing here? For those of you who do calculus, you don't actually have to remember derivatives and integrals. It's given to you on a formula sheet. So this is the advanced formula sheet from 2020, which is still going to be in effect for quite a few years. And so you just scroll down to the calculus section and you find the integral. So cos is one of the easier ones. The integral of cos is just sine. So that's what we'll do. All right, so actually I have all the answers on the side already, so I just copied them over because I was typing them up with Brooke. Right, so the integral of, so here we go. Right. Okay, so the integral between 0 and pi and 3 of cos x dx. So you first of all replace the function with its primitive, so in this case sine x, and then you take this function with the inputs of the upper boundary and the lower boundary. So in this case, the upper boundary is pi on 3 and the lower boundary is 0. Just a quick note about the upper boundary. Normally, you can just shove it into the calculator and get an answer. Make sure your calculator is in radians mode. But in this case, the question specifically asks for, I'll just zoom in a little bit. So in this case, the question specifically asks for exact value, which means you can't just jam in the calculator. So in this case, you're going to use the triangle they've given you at the start of the trig section. So at the start of the trig section, they give you a exact angle triangle. Pi on 3 is 60 degrees. So pi is 180. And so divided by 3 is 60. So you look at 60, you look at sine, which is opposite over adjacent. Opposite side to the 60 is root 2. Adjacent side to the 60 is 2. So here we have root 3 on 2. And sine of 0 is 0. That one you can check on a calculator. So the exact answer is root 3 on 2. So for part 2, using the trapezoidal rule with 3 function values, find an approximation to the integral. So this is the exact integral as before. So sorry, just give me a minute. Should have had the Zoom pen prepared. I'm just going to grab the Zoom annotate pen. All right, so this integral here is actually the same as this integral here. But we're not going to do the exact version with the integration. We're just going to do the trapezoidal rule. So the trapezoidal rule is at the end of the calculus section. It's right here. So the thing about trapezoidal rule is you have to make sure you use the correct n value. So I see a lot of students make the wrong substitution into n. So the n is actually the number of trapeziums, or sometimes they'll say number of intervals. So for this particular question, the question is actually phrased differently. It says 3 function values. So when you take 3 function values, you actually end up with only 2 trapeziums. So I'll show you what I mean. So we are integrating cos x. So cos x looks like this. So this point right here is 90 or pi on 2. So we are integrating it up until pi on 3. So we're integrating up until 60. So about here. Oh, that's not very good. Anyway, we're trying to find this area right here. So the idea is when you take 3 function values, that gets you the value of this point here, and this point here. And when you make trapeziums with those points, so there's a trapezium right there, and there's a trapezium right here. So when you make trapeziums with the points, you actually only end up with 2 trapeziums. And in the trapezoidal rule, I can barely say that because thanks to the Zoom scribble. All right, so in the trapezoidal rule, the n is the number of intervals or trapeziums. So don't confuse that with the number of function values. So anyway, for this particular question, you start out by doing a table of values. So I have that here. So you start out by doing a table of values like this. And it's color-coded. Well, I'll show you why in a second. And then you apply the trapezoidal rule formula. So here's the trapezoidal rule formula, right? So I kind of did it slightly in a cheating way, because normally you're supposed to go b, which is your endpoint, minus a, which is the starting point, over 2n. But as you can see, this value here, pi on 6 on 2, I kind of just did the height divided by 2. So in this particular case, the height value is not how tall your trapeziums are. It's actually how wide they are, because they are sideways trapeziums. So how far your trapeziums go along the x-axis is the height value. So the height value here is pi on 6, which is 30, because you're taking a estimation of between 0 and 60 using 2 trapeziums. So each trapezium is 30 tall, even though it's going across. So I just did pi on 6 over 2 as a cheating thing at the start. And then inside the trapezoidal rule, you want the starting value once and the ending value once and 2 of every middle value. So that's why this is color-coded. So 1 here is your starting value. That's how tall your trapezium is at the start. And a half here is your ending value. That's how tall. So I don't want to say height, because that confuses it with the age. That's how how far up the y-axis it is at the end. And then double of every middle value. There is only one middle value. It's root 3 on 2. So you just put it in here. There's a bit of algebraic manipulation required here. So you need to change this into one giant fraction, because they wouldn't really accept this answer, even though they did say leave your answers in terms of pi and root 3. And you can see it's like pi and root 3, but they're not going to take just a formula form. So there's a little bit of manipulation involved here. So 1 plus 1, so 1 plus a half is 1.5, or 3 on 2. So you can combine this 3 on 2. This part here actually cancels out to be just root 3. So you can combine both of those to be 3 plus 2 root 3 over 2. And then you can actually see that matches. So hold on, let me just write it out. So this part's 3 on 2, and then this part is just root 3. So if you turn it into, sorry about that. If you just turn it, so if you multiply top and bottom by 2, you can turn it into root 3 over 2. And then you can add them, because now there's a common denominator. So that actually ends up as being 3 plus 2 root 3 over 2. And this part here, 3 plus 2 root 3, it looks very suspiciously like something you're about to use in a second. So that's kind of a hint that you are on the right track. And once you combine the pi on 6 on 2, which is just pi on 12, and the 3 root 3 on 2, you end up with something that looks like this. Pi outside of 3 plus 2 root 3 on the numerator, and 24 on the denominator. That was 2 times the 12. Again, try to do that on your own, working out sheet of paper, if you're trying to figure out how you got from the second line to the third line. All right, so you just leave that. That is actually the exact version answer for part 2. So now on to part 3. So using parts 1 and 2 show that pi is approximately equal to whatever this is. And the reason why you do that is a tip I kind of wrote for a book. So when finding the same thing 2 different ways, you can see here, this and this are exactly the same, but we found it 2 different ways. In part 1, we found it through straight integration, and in part 2, we found it through an estimation with the trapezoidal rule. So both of those numbers are a way to express whatever this integral is. One of them is exact, and one of them is an estimation. That's why there's a squiggly equals here. So when you use parts 1 and 2, you just make them equal to each other. So the first line of your working out looks like this. So you take the root 3 on 2 from part 1, and you take the whatever this is from part 2, and you just make them equal to each other. And then you just do regular algebra. So from here on, you cross multiply, and then so I'll just give you the rest of the steps here. So if you like to try this at home, you can write down the working out and do it on a sheet of paper, but the rest is just straight up algebra. So I won't quite demonstrate it here. The 24 goes to the left, the 2 goes to the right, and then when you isolate the pi on its own on the right-hand side, you end up with the required answer, which is pi approximately equal to 12 root 3 over whatever that is. Because this thing here goes on the denominator, and the 24 and the 2 cancel out to be just a 12. So it does work. It is the required thing to be shown. So that's just that's just a question to probably get you to stop watching the video immediately, because this is quite complex. But stick with me. There's a couple more series and sequence questions coming up, which I think have interesting presentation. All right, next one. We have a question from the financial math section of the paper, but really just a series. So for this one, which expression is a term for the geometric series? Blah. So whenever you get a geometric series, you want to identify the A and the R. So if you look in the series and sequence section, right, so this is the series and sequence section from the formula sheet. And if you notice that they just have, this is this is arithmetic. So we're looking at this section. So every single formula has an A and an R. So we want those things before we start working with any of the formulas. So let's do that. So let's identify the A and the R. So I kind of did it in the wrong way in the notes I pre-prepared. So it should actually say it this way. Let's do the starting term first and then the common ratio. So the A is the starting term of the series, in this case 3x. And the common ratio is negative 2x, right? So the minus is very important. For those of you who do tutor maths with me, you will know that I have a very narrative approach to maths tutoring. I like to just randomly have sentences to remind you of stuff. So here, the common ratio, you can see the signs of the terms are flipping around. So it goes from negative to positive to negative, and that's because you are multiplying by a negative number. So the x's are going up by a power of x, so that's the x here. And then the 3 is going to be multiplied to minus 2 to get minus 6. And then minus 6 times minus 2 is plus 12, so the number part is minus 2. So the common ratio altogether is minus 2x. And from there on, you can just do trial and error if you like. You can. So we're trying to find which expression is a term. So we're looking for a particular term. So we're using the t subscript n is equal to ar n minus 1 formula. So this is what I have on the side. So we're just using that formula. And you can do a bit of trial and error, but hopefully you're cluey enough to figure out which term you need to find, right? So the way Brooke and I did it like in class is I showed her the 10th term, and it was none of those. And then we did the 11th term, and it was the thing here, which is option C. But hopefully it's just the fact that you need to identify what this number needs to be. So if you just have a look at the pattern, the first term has a power of 1 here. The second term has a power of 2 here. The third term has a power of 3 here. So I mean, I guess you don't really know, right? Like because of this number, it doesn't really tell you which term you want. So, you probably do need to do a bit of trial and error. There is a way to not do trial and error. You take their number, 3072, you divide it by 3, then you do log 1024, which is the answer there, divided by log 2 to know that it is in fact a, so it should be like this. It should be it's actually 2 to the 10th power. But it doesn't quite help you really. 2 to the 10th power is actually the 11th term. But yeah, so just apply the term formula. Just pick one of those. You can actually knock out 2 of them already because every even numbered term has, if you look at the powers, every even numbered term has a negative in front of it, and then every odd numbered term is positive. So this is x to the power of 1. So you can actually just knock out. So this even numbered term is not negative, so that's wrong. This odd numbered term has a negative, so that's wrong. So just judge one of these guys. So yeah, just work out the 10th term and the 11th term, and you'll see what's up. The 10th term is actually like 3 times smaller than this, so 1024. Oh no, that's not right. Yeah, so just put in the formula for the 11th term. So substitute 11 here, so n minus 1, so 11 minus 1, and then put the common ratio here. And then when you do this kind of stuff, make sure you put this into your calculator with the brackets, right? So if you just enter into a calculator minus 2 to the power of 10, your calculator actually spits out negative 1024. That is not the answer, because your calculator thinks you want the negative version of 2 to the power of 10, and that's not what you want. So you want to do some brackets. So you want to do left bracket, minus 2, right bracket, power of 10, and the calculator will spit out positive 1024. And you multiply that to the 3 to get this number here. And then this is x to the power of 1 multiplied to x to the power of 10, and that's why it's x to the power of 1. All right, so let's look at a different question. So this one here, it's very unusual. So like I was kind of harsh on this question. Like I'll just write out all my notes here and I'll just explain it. So these are the notes we had. It's kind of like a trial and error kind of thing. So let's actually talk about this further. So the graph above shows the first 6 terms of a sequence, and it's graphed in kind of an unusual way, because when you see a linear, like a bivariate graph like this, you see x on the horizontal axis and y on the vertical axis. Here on the horizontal axis they have n, and on the vertical axis they have t of it, t subscript f, so which term it is. And it's just like 1, 1, 1, 1, 1, 1. So these are the notes we had on the side. So I wrote to help with this stupid question because I don't like it. This question has a very unusual presentation. So I just told her to write out the full sequence. So the sequence is 1, 1, 1, 1, 1, 1. So once you have the so you can read the n-axis as which term it is, and the t-n-axis as what value is that term. So the first term is 1, has a value of 1. The second term has a value of 1. The third term has a value of 1. So it's all 1s. So once you have the sequence, just do a trial and error thing with all the words to see which ones are wrong, like all the sentences, right? So A is wrong because that sums to 1. So the sequence is 1s for, it's not actually, I told Brooke that it's forever. It's actually not technically forever. It could just end here, but whatever. No matter if it goes forever or ends there, the sum is not 1. If it ends right there, the sum will be 6. If it goes on forever, the sum will be infinite. So no matter what, it's not 1. So that's wrong. An arithmetic sequence with the common difference of 1. Well, first of all, this is not even an arithmetic sequence. I guess it could be, because the common difference could be 0. So yeah, it could be. But then but here the common difference is not 1, right? So the difference between the terms is nothing. So going from the first term to the next term, you've added nothing. So that's 0. And then a geometric sequence with an infinite sum of 1. So the sum, if you actually add it up, again, they are all 1s, so it's infinite. And it doesn't actually have an infinite sum, because to have an infinite sum, the ratio has to be, you can actually see it on the formula sheet, the ratio has to be less than 1. Right? So we're looking at this section here. The absolute value of the ratio has to be less than 1. So the ratio here is exactly 1, so it doesn't have a sum. So the sum is infinite, because you're adding a bunch of 1s together, so it eventually becomes infinite. And then finally, because we're doing process of elimination, the last one is correct. And then again, you can see I don't like this question. I just wrote, even though the sequence is useless. All right, moving on. So for this question, we have the first term of a geometric series is A, and then A is less than 0. So again, when you read less than 0, just try to generalize it. So it's a negative number. So it's just any negative number. And then, so it could be a fraction, could not be a fraction, doesn't really matter. And the common ratio of this sequence R is such that R is less than -1. So again, it's a negative number that's bigger than -1. So negative 1.1 all the way up to negative infinity, something like that. And then which one of the following graphs best shows the first 10 terms of the sequence? Right. So this is again slightly unusual presentation. So I just so for the notes I was writing, I just had a bunch of I just had a bunch of kind of facts about sequence and series in general, which I try not to do, because when I do tutoring, I try not to sound like a textbook. But what I had here was, if the ratio is between -1 and 1, it means you're multiplying by a fraction. right? So anything that's between negative and 1 is like a fraction that's smaller than 1. Like technically anything's a fraction. 42 over 2 is a fraction, and that's the number 21. Anyway, but you're multiplying it by a less than 1 fraction. 3/5, 4/7, 5/8, something like that. So when you're multiplying by a fraction smaller than 1, the number is getting smaller. So then when every subsequent number gets smaller than the previous number, you can actually add it up. There will be a limiting sum somewhere down the line, right? So that's if the ratio is between -1 and 1. So it's like a fraction that is smaller than 1. Doesn't matter positive or negative. But if the ratio is smaller than -1 or bigger than 1, so it's like a number that's bigger than 1, so it's not a fraction, you actually multiply it by something that makes the number bigger, then the series is what's called divergent, so it doesn't have a sum. I mean, well, this question is not even about sums, but yeah, here are just a bunch of general facts about convergent and divergent. All right, so let's think about how with this particular question. So the number is less than -1, which is here, if r is smaller than -1. So every term is getting bigger, but the thing you have to consider here is that with a negative ratio number, right? So if the ratio number is negative, the values for the numbers in the series actually flip-flops on either side of the x-axis. So depending on positive, negative, positive, negative, positive, negative. And that's it's actually, you can see that from this question above, right? So here the ratio is -2x, which is a negative number. And then you can see the series goes from negative to positive. The next one is negative. The one after that will be positive, and so on. So this particular series will go on either side of the x-axis. That kind of knocks out C. And really D as well. You can see D is converging upon a value. So it's getting smaller and smaller towards a certain value. So C and D are both out. So we're looking at between A and B. So A and B both have like the right qualities. So they start with the first thing on the bottom of the axis, that's negative. That's good, because we said the starting term is negative. And then it goes to above it, then below it, then above it, then below it. So the differentiating factor between A and B is that A is linear. So these numbers are going up by a steady rate, and that is not what a geometric series is. So whenever you're multiplying by a number that is not a fraction, it will get bigger at a bigger rate. So if you do functions, it will be increasing at an increasing rate. So it wouldn't be increasing at a flat rate like this, no matter if the number is bigger than 1 or -1. So yeah, so in this case, I just did one random example. So if the starting term is 1 and the common ratio is -2, which is a number that's smaller than -1, it will get something that looks like this: 1, -2, 4, -8, and 16, right? Because starting term is 1. I mean, I probably should have started at -1 because A is negative. But yeah, as you can see for this sequence, right? So 1, and then it goes to -2, and it goes to +4, and it goes to -8, and then it goes to +16, like way off the chart, right? So it goes up by an increasing rate. That will just be one random example. So the answer here is B. So again, my very casual explanation. It's the correct flip-flopping and the correct shape because it gets wider. All right, moving on. We have a very unusual question here. I do like it though. It's a very real-life relevant. So an artist posted a song online. Each day there were 2n plus n downloads, where n is the number of days after the song was posted. And we'll just do two different parts on the number of downloads on each of the first 3 days, and what is the total number required. So part 1 is not that problematic. Part 1, you just do a table of values, which I've done over here. Okay, so that's part 1. You just have n is number of days, 1, 2, and 3. D as downloads. That's just the thing I like to do personally. Some people just like to do X and Y. That's fine also. I like to use the letter of whatever it is representing. And you just substitute them into the formula. So for 1, it's 2 to the power of 1 plus 1. So that's 2 plus 1, that's 3. For 2, it's 2 to the power of 2 plus 2. So that's 4 plus 2, that's 6. For 3, that's 2 to the power of 3 plus 3. So that's 8 plus 3, that's 11. So that's the table of values here. So for part 2, it is a little bit unusual. What is the total number of songs the song was downloaded in the first 20 days after it was posted? So for this particular question, if you look at this series here, it is neither arithmetic nor geometric, right? So arithmetic series are strictly just adding on the same number every time. And geometric series are strictly multiplying by the same number every time. And 2 to the power of n plus n is neither of those things. So even though when you see the word total number, right, you might be like, oh, I'm going to go to my formula sheet. I'm going to do one of these sum formulas, right? But what's actually happening is you can't choose one to do. So it's like, oh, do I use the one for the geometric one, or do I do the one for the geometric is down here? Do I do the one for the geometric one, or do I do the one for the arithmetic one? The answer is you do both. So you probably already got spoiled by this highlighting. But anyway, so when you have 2n plus n, it's actually 2 separate series. So I joined the graph that I was doing. Right, so let's say let's say days, sorry, number of days, and then downloads, right? So on the so let's do downloads over here and number of days over here. So why did I write it so far above the line? Let's try it again. So downloads and then the number of days. All right, so on the first day, right, so it's 2 to the power of 1 and then a 1 here plus it. And on the second day, it's 2 to the power of 2 plus a 2 here. And on the third day, it's 2 to the power of 3 plus a 3 here. And it goes all the way down to 20. So 2 to the power of 20 plus a 20. So the idea is you actually have to like split it down the middle right here. So on the right is a geometric sequence. Arithmetic sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 20. And on the left is a geometric sequence, 2 to the power of 1, 2 to the 2, 2 squared, 2 cubed, 2 to the power of 4, 2 to the power of 5. Right? So there are two separate series here. So if you just try to look at this thing like as one continuous block, you can't do anything to it. So you're going to split it up mentally because you're adding them all anyway. Right? Because these are pluses in the middle. You are adding them up anyway. So you can just add up everything on the left side and then add up everything on the right side, and you will be adding up everything in that section of the table. So that's how you approach this question. So the actual mechanics of it is not that different. It's difficult. It's just the presentation of it is hard, right? So at this stage, like, Brooke and I were running out of sort of tutoring time, so we didn't even do it. I just wrote down what you have to do. So you apply the sum formula to the 2 to the power of n for days 1 to 20. And then you apply the sum formula to the n part for days 1 to 20. So it's actually an arithmetic sequence with a starting term of 1 and a common difference of 1. So you just apply the formula. And then you add those two results and you will have the total number of downloads. So that's that one. Here, so express the recurring decimal 0.323232 repeating as a fraction. So for those of you who might remember this from primary school, anything repeating is just a number of repeating digits over that many nines. So for example, if you want to try like 0.147147, you can try this right now. Grab a calculator, just do 147 over 999, and you'll get 147, 147, 147. Sadly, for this question, you don't get to just use that fact. You're going to still do it in a series way. So you can see here, all right, I already spoiled the answer. All right, so up here, so this is actually a geometric series sum, right? So the first term in the series is, I'll write this out. The first term in the series is 0.32. The second term in the series is 0.0032. The third term in the series is 0.000032, and it just goes on. And when you add all of these terms up, conveniently, right? So because this is all zeros here, so this 32 just goes here, and then becomes 3232. And then when you add these two together, it's 3232. But when you add it to the third one, this 3232 conveniently goes where these four zeros are. So it's now 323232, right? So that's how that's where the series comes from. So that's the geometric series. And you just apply the series sum, which I think I have here. Yep. So because the common ratio is less than 1, you can see it's a fraction, 1 over 100. So you can use the sum formula. That's the one right at the end, right? So this is, there are two different sum formulas here. Just remember that this one is the sum up to a specific term. So the sum up to the 50th term, the sum up to the 400th term. This one is the limiting sum. So this only works when you have a common ratio that is a fraction that is smaller than 1, either on the positive or negative side. And then this will limit to something because the numbers get smaller and smaller and it's convergent. It will converge on a value. So right now we want the convergent sum. So, stamp, no. So you substitute the values into the convergent sum formula. The starting term A is 32 over 100. So you can try to, because it's fractions, don't just do decimals. And the ratio is 1 over 100. So you can see on the bottom, 1 take 1 over 100. So when you can just jam this straight into the calculator. You can actually just jam 0.3232 in the calculator and press the fraction button, but let's not do that. But that's one way that you can check that your answer is correct. Anyway, it'll just spit out 32 over 99, which is the answer for that one. Finally, lucky last, we have, again, you can see here the exclamation mark. So it's like everyone did very poorly on this question. So you should watch out for the complexity. So again, a lot of these questions, they're not necessarily hard because the maths is hard. They're hard because the approach is hard. You have to think about it in a certain way. But once you get through the shroud of complexity, the actual calculations are not overly difficult, unless it's calculus. All right, so let's try to see through the shroud. So by summing up the geometric series 1 plus whatever, or otherwise, find the limiting sum. So the idea is when you find the limiting sum, find the limits, right? It's not a sum. Find the limit as x approaches 1. So normally when you find the limit, all you do is just replace the x with the 1. So like if I want to find the limit as x approaches 1, I just replace this x with a 1 and then replace this x with a 1. However, that is not something you can do here, because once you do that, you get 1 minus 1 on the denominator, and that's a 0. And you can't divide by 0. That's just not a thing in maths. So sadly we can't just do it as simply as just swap out the x for a 1. Unlucky. So let's do what they said. So by the way, when you guys see a question like by doing something something or otherwise, just do the something something. It's like those hence or otherwise questions. Always do hence. Otherwise does work, especially in extension maths. You'll see this a lot in extensions 1 and 2. I frequently did, humble brag by the way, I did extension 2. I frequently did my extension 2 answers with otherwise, just because some cool trick I learned in class or saw online or heard from my teacher or something. But just in general maths exams, when they tell you to do something, just do it. There's no otherwise. So we are going to do the exact thing that they said. So we're going to sum up that series. Okay, so I have it right here. Oh, that's not good. Yeah, okay, here we go, got it. All right, so we're applying the summation formula up to a certain term, right? So we want it up to the 5th term. So there are 2 different ones here. So make sure you choose the one that matches up your question. So again, just glance down at the part below. You're like, oh, okay, I want x on the left and 1 on the right. So there are 2 different versions here, right? So you can see it's either equal to this or equal to this. So you want to pick the one that is better for your question. So we're going to use this one because it has the ratio, which is x on the left and 1 on the right. So that's the one you want to do. All right, so let's do that. So with this particular series, the first term is a 1. The common ratio is an x. So that's when you multiply to every term to get to the next term. And just like jamming in the formula, right? So the sum up to 5 is, so we're using the right formula, remember? So r, so here the ratio is x, to the power of n. So we want the 5th term. So just power of 5. Take away 1. Oh, yeah, a is 1, by the way. And then over r minus 1, so x minus 1. And then you just expand out the bracket. The most difficult expansion you'll ever see is like, I want to multiply 1 to the first term. And I want to multiply 1 to the second term. All right, so now you ended up with something that matches what they want, right? So this matches this exactly. So how do you use it? Well, the idea is you can just, because this is actually the same as the sum, you can just, it goes all the way back. So this is what we call cyclical structure in writing analysis. When finding the same thing 2 different ways, can treat both answers as equal to each other. So because we just found this sum for this expression, hold on, I'll use, I always use word highlighting, I use Zoom annotation service. So by finding this sum for this expression, they are the same thing, right? They are equal to each other. So they sum up to 5 because there are pluses in here, So it's not just a series. This is an expression when you're already adding it up. So these 2 are exactly the same. So what you can do when they're exactly the same, you can replace this with this instead. And that solves your problem of having an x minus 1 on the bottom, right? Because before, the whole problem with this limit, because normally with limit, you just swap out the number. But the whole problem is I can't swap this for a 1 because I end up with 0 on the bottom. So by replacing this with this, you solve your problem of not having 0 on the denominator. So let's get rid of that. So the rest of the question is you simply replace it. So I've got it tapped up here already. Sorry, 1 second. Okay, so over here. All right. So once it is, so instead of taking the limit of the fractional expression, exponential thing, you're actually just taking the limit of, I actually had it wrong, so this should go here. So you're actually just taking the limit of this thing. And then this is a situation where you can just replace the x for a 1 because there's no maths laws being broken here. You're not dividing by 0. And you just replace it all with 1. So it's 1 plus 1 plus 1 plus 1 equals 5. So as you can see, any question that's hard, like this question, you can see bottom 9%, right? So it's a very hard question. But like, look at what you're doing. You're doing 1 plus 1 5 times. So the actual maths isn't hard. It's the layers of complexity that shroud the question. That is hard. So try to see through that. All right, and that's about it today. I wonder how many of you would have stuck it out to the end, because I know that all of my subs are all my students, and not all of you are in Year 12, and not all of you do advanced. So I wonder how many of you stuck it out. So for those of you who did stick it out, please tell me what you thought of this format. Would you like to see me? Which is kind of weird though, because that's what you do with me anyway. But anyway, let me know if this was helpful, or you would like to see a Zoom lesson where I just literally break stuff down, so that it can be recorded somewhere, and maybe other people might find it useful. Yeah, so please, like, I know I ask for comments all the time, and I don't usually get them, and that's fine. But this time, I would really love some comments about what you thought about this particular format. So yeah, please let me know. Thanks everyone for watching. There's no intro and outro because I'm not even going to edit this. I'm just going to upload the Zoom recording. Until next time, keep learning and take care. All right, where's the stop recording button? Here we go. Where is the stop recording button? Is it here? Here? Oh, there we go. All right, okay. Bye, everybody.